Yeah, I'm Arthur. I'm going to talk about our paper, Compositionality and Observational Refinement for Linearizability with Crashes. This is in collaboration with a bunch of folk from the Flint group at Yale, including Zhongye, Wang, Yixuan, Chen, Peixin. Okay, so the setting for the paper is concurrent computation with full system crashes. Full system crashes is something like holding the power button for too long, a OS failure, a power outage, a critical component failure. And in terms of what this looks like for the observations of these systems, we will have a usual trace of a concurrent object, and then a crash. Once a crash happens, the system goes to idle, and then every component of the system is ready to take a call. So in this context, in addition to the concurrency, you also have to specify what happens to these objects when a crash happens. Some examples, all of which are memory cells where you can read and write, are, for example, a volatile memory cell where if you write one, you will read one, but then when a crash happens, you go back to the initial state where you read a 0. Meanwhile, if it was a persistent cell, then after the crash, you would read a 1. And for a more realistic interface, you would have a memory interface where, let's say you write a 1, you have access to an operation which flushes that write so that it persists to the rest of the system. And then you could write a 2, you would read a 2, but then if a crash happens, you don't know if you're going to read a 1 or a 2 because you haven't flushed that write, and you don't know if the hardware has non-deterministically flushed it for you. So in addition to specifying the crash behaviors, you also need some mechanism to specify these objects under concurrency. Usually, one way to do it would be to use linearizability, which would allow you to reduce the behaviors of the program down to a sequential behavior. In the context of crashes, a popular version of linearizability that includes the crashes is durable linearizability, which works very simply by first removing the crashes and then just linearizing as usual. And the linearization will allow you to reorder some operations, complete some pending calls, remove some pending calls that haven't taken effect, all to get into this sequential behavior of a usual memory cell. So in our paper, we present a compositional model of computation with crashes. What this means is that it comes with a horizontal composition operation that allows the client to use both components at the same time, a vertical composition which allows you to compose implementations. So if you implement an object B with an object A, an object C with an object B, then you can implement the object C with the object A by composing the two implementations. And a notion of refinement. What it means for this to be compositional is that all of these operations come with several algebraic properties, like the fact that horizontal and vertical composition freely distribute, that the operations are monotonic with respect to refinement, and so on. Then we extend this compositional structure through several linearizability criteria with crashes. And we also present a rely guarantee-based program logic that is sound with respect to this linearizability criteria, so you can verify individual components. To make this more concrete, I will go over one of the main examples that we cover in the paper, which is a library for guaranteeing persistence of memory. So imagine you have a system which only provides non-volatile memory. Non-volatile memory is challenging to program because of the non-determinism caused by the non-deterministic flushes performed by the hardware. So it's common practice to provide a library that will manage the flushes for its clients, and then it will provide the illusion of having persistent memory instead. One such library is the Flit library, which I have a simplified version of here. And the way it manages these flushes is that whenever you try to make a store, it will increment a counter dedicated to that location. It will do the store, then it will try to flush, and then if it succeeds with the flush, it will decrement it. The point being that if you successfully store, you definitely have flushed that store. Meanwhile, a load will first load, and then it will check if the counter for that location is non-zero, because then that means that there is an ongoing store to that location that has not flushed yet, and then it will flush and then return. So that means that any load that returns a value that has been flushed at some point. So the authors of the paper claim that if you use this library and then you implement on top of it some object that is linearizable without crashes, then the library guarantees it will be durably linearizable. But consider how we would state this theorem if we had the language to do so. It would have to say that for any object type, for any implementation, if you compose this implementation with the specification of your memory, and then you prove that's linearizable to something, then if you linked that with the library, and then you provided crash semantics to this instead, combined it with non-volatile memory instead of the usual memory, then that would be durably linearizable to the same library. This is a quite challenging statement to write. In addition to prove, it's much worse, because it's quantifying over any object, any implementation. It's relating a correctness property without crashes to one with crashes, which involves two different semantics. But even then, you're not even using the same code anymore because you have linked it with this library, and you have changed the underlying objects that are being used. And to make matters worse, while the correctness is stated in terms of durable linearizability, you will struggle to use durable linearizability to specify the rest of the system below that, which is a point I will make now. So if we were in a setting without crashes, the way we would specify a memory array would be by using this property of linearizability that if you know an object is linearizable to something, and then some other object is linearizable to its specification, then their horizontal composition is linearizable to the horizontal composition of the specifications. So then the memory itself would be specified by horizontally composing the specification of each cell. And in this way, you would obtain exactly the same specification you would get if you had just specified the memory array as a whole. So if we try to do that with durable linearizability, we could pick a trace of a volatile or buffered cell where you just write one, and then you read one, and then a crash happens, and then you read a 0. If you have a different location and you perform the same operations, then those would be durably linearizable to the traces without the crashes because the traces are already sequential. So if you then try to horizontally compose them together, at the level of the specifications, which don't have the crashes, you would be allowed to write to the two locations, read twice the first location, and then you would read a 1 and a 0, and then read the second location where you would also read a 1 and a 0. The problem is that in the real system, you never read a 0 and then a 1 because they only reset at the same time when the crash crashes the entire system. So the specification is over-approximating those behaviors. And it could be very important to a client that you know that all the locations have reinitialized at the same time. So to deal with this, we propose crash-aware linearizability, which uses crashes at the level of specifications as well, so that you're better able to specify the crash safety of these components even after you linearize. So the criterion would instead synchronize the crashes and then linearize at the level of each epoch. Because the composition operations, they manipulate the crashes as well, the horizontal composition synchronizes the crashes, which means that at the level of specifications with crash-aware linearizability, the horizontal composition first synchronizes the crashes and then horizontally composes each epoch, which allows us to specify the non-volatile memory by horizontal composition, just like you would be able to do under the usual linearizability. But the point is not that it's better than durable linearizability. The two are very useful. It's just that crash-aware linearizability is somehow more fundamental, and then when you need the durable linearizability, you can use it. This is enabled by a little lemma we prove, which shows that if you first crash-aware linearize and then you durably linearize, you actually have just proven durable linearizability itself. So more broadly, durable linearizability is useful because it provides specifications without crashes. It has a very strong observational refinement property, as I will mention later, and which makes it great for persistent objects, but it struggles with weaker crash behaviors. Meanwhile, crash-aware linearizability, it's better for composition. It's good for specifying more subtle crash behaviors, but it struggles with some more complicated recovery schemes that durable linearizability is very good for. So to verify the full library, we go into several parts by using the fact that we have a compositional model. The first part is the fact that we can split the verification of the library to the individual locations because they only operate over a single location at a time. And this is only enabled because we can define the non-volatile memory by horizontal composition. Then we have a program logic that we use to verify that the code is correct at the level of each location. And this is just a relay guarantee logic. The top level rule asks that you prove the usual obligation that the guarantee is contained in the relay. but then you also have to show that every method is correct against its linearizability specification. When you crash, the recovery correctly restores the object invariant. And the program logic is sound with respect to all the crash linearizability criteria we consider. Then, by using horizontal composition, which is part of the model, it's not just part of the linearizability, we compose the implementation at the level of each location to obtain a correct implementation of a persistent memory using the fleet library. Then we prove this observational refinement property for durable linearizability, which says that that an object is durably linearizable if and only if for any client you pick, if you show it's linearizable without crashes to something, then after you add the crash semantics to the code, then it is durably linearizable to the same thing. If you combine what we have done so far, that already means that because the fleet is correctly implements a durably linearizable memory array, that if you put any client on top and you show that's linearizable to something, then by adding crash semantics, it would be durably linearizable to the same specification. The final step is to use vertical composition to compose the client with the library to obtain that the composition itself is correct on top of the non-volatile memory, not just on top of the interface provided by the library. And that's how we obtain the correctness theorem I showed earlier. We exemplify the use of the correctness of the library by verifying a snapshot object that would be used in, let's say, a distributed system. And this object does not admit an atomic spec, which also shows that we have generalized this linearizability criteria beyond just atomic specifications. And then we compose it on top to obtain a persistent snapshot object under full system crashes. So in summary, you should check the paper for all of these results. There is a very detailed technical treatment of how we obtain all of these strong properties about this linearizability criteria. There is also a longer example with just crash-aware linearizability, which shows that it can handle a variety of crash safety specifications. Yeah, thank you.